Good day to you, students. How are you doing? Today, we'll be dealing with chapter 18.1, electrical quantities. Now, the subheading we have here is what? Current in electrical circuits and electrical resistance. Let's start the class. Now, current in electrical circuits. We have to drag the words into the correct boxes. If an electric current is to flow, two things are needed: a complete circuit for it to flow around and something to push it around the circuit. The push might be provided by a cell, battery, or power supply. A battery is a combination of two or more cells connected end to end. In most circuits, metals such as copper or steel provide the circuit for the current to flow around. When a switch is closed, the current flows along a continuous metal path. Let's check. That's correct. Now, let's deal with good and bad conductors. Let's start. Wires are used to connect circuits, are made from metals which are good conductors of electricity. The metals are usually surrounded by plastics. Plastics are good electrical insulators. Good conductors include copper, silver, gold, and steel. While good insulators are polymers, minerals, and glass. Also, liquids may conduct electricity but not very well. We check. That's correct. Now, electric current. You have to fill in the missing words so that we can have a full definition of what electric current is. When a circuit is complete, electric current flows. Current flows from the positive terminal of the supply around the circuit and back to the negative terminal. What goes around the circuit is electric charge. A current is a flow of electric charge. In a metal, the current is a flow of electrons. To measure an electric current, an ammeter, like this, is used. An ammeter is connected to a circuit in series. To add an ammeter to a circuit, the circuit must be broken. In a simple series circuit, it does not matter where the ammeter is added, since the current is the same all around the circuit. The unit of electric current is the ampere, which is denoted or represented with the letter capital A. So check. That's correct. Now, more current and electrons. We are also to fill in the missing wedge. Metals are good electrical conductors because they contain electrons, just like we've been mentioned in the former slide, that can move about freely. In a bad conductor, all the electrons are tightly bound within the atoms or molecules in such a way that they cannot move. While most of the electrons in a metal are tightly bound within the atoms, so are free to move and within the material. These are called conduction electrons. Okay, voltage in cardinal or capital letter first starts the conduction electrons moving in one direction through the metal, which makes electric current to flow. Since electrons have a negative electric charge, they are attracted to the positive terminals of the battery. For a conventional current flow, electrons move from a negative terminal to the positive terminal of the battery, while a positive charge moves from the positive terminal to the negative terminal. Let's check. Dash option. Now, current and charge. How is current related to charge? Let's find out. An ammeter, okay, measures the rate at which electric charge flows past a point in a circuit. It is the amount of charge that passes per second. The equation between current and charge can be written as I representing current is equal to Q represents charge per unit time. That is T representing time. Now the unit as what? Coulomb per seconds or amperes. Whereas charge Q is equal to current multiplied by time. Let's check. That is it. Now we have this question. Let's solve it together. Okay? A current of 150 milliampere flows around a circuit for 1 minute. How much electric charge flows around the circuit in this time? Don't forget from the previous slide that you have I is equal to what? Q over T. Let's move from the known to the unknown. You have to look for Q. Q is what? IT by way of subject of formula. So our Q, our I now is 150 milliampere. And whenever you have the word milli, that means 10 raised to the power minus 3. So 150 times 10 raised to the power minus 3 ampere now. Now, time is 60 seconds. That is what? 1 minute. Okay? So, don't forget that time will always be what? Measured in seconds. That is standard. But here we are given what? 1 minute, which is converted to what? Seconds. So, our Q now will now be I 150 times 10 raised to the power minus 3 times what? 60. Now, Q is equal to, if you look at it, 15 times 6 is what? 90. Alright, there is a 0 here, there is another 0 there, multiplied by 10 raised to the power what? minus 3. But let's convert 9,000 to what? A mere of standard form. That will be 9 times 10 raised to power what? 3 times 10 raised to power what? Minus 3. Now, if you have 3 and minus 3, that will be 3 minus 3 is what? 0, right? Now, 9 times 10 raised to power what? 0. 10 raised to power 0 is what? 1. That will be 9 times 1. And that gives us what? Our Q now is what? 9 coulombs. So, coulombs is the unit of what? Charge. Don't forget about that. So, from our option now, let's pick 9 coulombs and see. That is it. Now, I've already prepared a way for you to be able to check the procedures. I, 150 milliampere, T is 1 minute into 60 seconds. And if you look at Q, the same process followed. We arrived at what? 9 coulombs. Now, let's deal with electrical resistance. We have to fill in the missing words. The current flowing in a circuit can be controlled by adding components with electrical resistance to the circuit. Okay? The greater the resistance, the smaller the current that will flow. A cell provides the voltage needed to push the current through the resistor. Voltage is rather termed as potential difference. Which flows across a resistor. Potential difference is measured in volts using a voltmeter. The resistance of an electrical component is measured in ohms. And it is defined as R, which is the resistance, is equal to what? V divided by I. That is voltage divided by what? The current. Current flowing through the resistor is measured with the use of the ammeter and connected in series. While the potential difference is measured with the use of voltmeter connected parallel across it. Let's check. Now, looking at this question again, okay, a resistor allows the current of 0.02 ampere to flow through it when there is a potential difference of 10 volts between its ends. What is its resistance? Don't forget that what? R is equal to what? V over I. So let's go from what? The known to the unknown. Our I is 0.02 ampere, while V is what? 10 volts. With that, R becomes 10 divided by 0.02. Then we have, we shifting the decimal point here for the denominator, 1, 2. That means I can have this, and this. By the time I shift 2 decimal points, I will have 2 0 with the numerator. Then I have over 2. Then R becomes what? 500 ohms. Is it part of the option? So let's pick it down and see. That is it. So I already have it prepared also here. If you want to check the procedure properly, you have R is equal to 10 over 0.02. That's 10 over 2 times 10 is to the power minus 2. By the time 10 divides to that's 5, but by the time the power to the denominator goes to the what? Numerator becomes 10 raised to the power 2. That gives us 500 ohms. Now, changing current. We are also fulfilling the missing words to be able to define how to change current. The greater the resistance in the circuit, the smaller the current that would flow. The greater the potential difference, okay, that's the voltage. And a circuit, the greater the current that will what? Flow. The longer a wire, the greater the resistance. The greater the diameter of a wire, the smaller the resistance. Let's check. That is it. Now, let's do this calculation. The option shows the voltage and current ratings for 4 light bulbs. Alright? Which bulb has the greatest resistance when used normally? So here we'll calculate the resistance of each bulb before we pick the best option. Now, let's start. For the 12 volts and 1 ampere bulb, we want to check the resistance. Resistance now becomes V over I, and that is 12 over 1. That gives us 12 ohms. Now, for the second one, this is A, this is B. Now, we have R is equal to V over I, and our V is 6, while I is 12. That is 0.5 ohms. That is very, very small. So let's check for option C. We have R, V over I, and that is 3 over 0.2. Now let's write out the 30 over what? 2. That's 15 ohms. I think that's larger. Now let's check for the third one. We still have 4 rather V over I. That is 2 over 0.5. More like 20 over 5. R is what? 4 ohms. So if you look at 12 ohms, 0.5 ohms, 4 ohms, and 15 ohms, you can see that 15 ohms is what? Larger. Which voltage is attached? 3 volts, and current 0.2 amperes. So we pick that and check. That is it. Now the solution also lies here, where you have it stated. So the one that is the highest, that is one I have marked that has 15 ohms. Now let's deal with this question also. A polythene rod repels an inflated balloon hanging from a nylon thread. What charge must the rod and the balloon carry? Now let's look at it again. A polythene rod repels an inflated balloon hanging from a nylon thread. What charge must the rod and the balloon carry? The rod itself carries the same charge as the what? Balloon. So they are going to do what? They are going to repel, in the sense that the rod and the balloon carries like charges. So that is what is going to what? Happen. The rod and the balloon carry like charges, as you can see. Now, let's deal with some electrical representation. Now, when you see a cell, or you see the diagram of a cell, this is it. It's going to have the negative terminal and also the positive terminal. For a resistor, this is its typical representation. If you should have a variable resistor, it's going to look more like this. Let me show you. Okay, it's going to look more like this for a variable resistor. Something like this. Okay, this dictates the what direction of the current or voltage. But for a lamp, we have this also. For an ammeter, don't forget that the unit of current is ampere, so we represent it with A. For voltage, unit is volt, we represent it with what? With V. Now, let's deal with this question. Okay? A student makes the circuit show. The fuse has blown and stopped the current. What could have caused this? The current was too large, the voltage was too small, the current rating of the fuse was too what? High, the lamp was loose. Now, a fuse will always blow when the current is too what? Is too large. That means by the time the current is large, the voltage might be small or big depending on the appliance that is in what? Question. So normally the voltage will have been too what? Large. Let's check. That is it. Now let's choose from this statement. We choose the correct statement. The greater the resistance in a circuit, the smaller the current that will flow. That statement is correct. It's coming from the point of R is equal to V over I. You know what we are typically trying to say here is that what? The resistance is inversely proportional to the current. So if resistance is higher, current will be what? Lower or smaller. Let's look at the seventh statement. The greater the resistance in a cycle, the greater the current that flows. It's like saying that resistance and current are directly proportional. No, that is not possible. The lower the resistance in a circuit, the greater the potential difference that is obtained in that circuit. No, as when resistance is higher, voltage will always be what? Higher, because they are directly proportional. So our best option will be that the greater the resistance, the smaller the current that flows. And also, for the last one, let's check the best out of this three statements. Current is measured in volts. That is wrong. It is voltage that is measured in volts. Current is measured in amperes. Now, resistance flows from the positive terminal of the supply around the circuit and back to the negative terminal. That is wrong. That is basically what? Current. So let's check this last statement. Current flows from the positive terminal of the supply around the circuit and back to the negative terminal. This statement is what? Fully correct. So we pick it. With this, we've come to the end of this class. Do well to join our website www.edubbey.com for more of our interactive books and videos. We also want you to subscribe to our YouTube channel. Subscribe. Bye for now.